It's my pleasure to open the talk of Andrej Bauer. Bauer is a professor of computational mathematics at the University of Ljubljana here in Slovenia. His work is on the foundation of mathematics, computable and constructive mathematics, type theory, and programming languages. He's particularly known for his work on homotopy type theory and programming with algebraic effects. He's also interested in mathematical art, and you can see some of his and his students' work at the exhibition in Portorož. He will be speaking on the dawn of formalized mathematics.
Thank you. Let's see if I can get this thing working. I should probably do this one. Okay, can everybody see my slides?
Yes.
Yes, it's okay. Okay. Hi, everyone. It's a great honor for me to have the opportunity to address this audience today. And I decided to tell you about formalized mathematics. It's something I've been working on for a while now. And I think it's an important topic. And also, my talk is going to be non-technical. I don't think it's appropriate to try to flex muscles at such a forum and do technically demanding things. But I would instead like to present something that I think is going to be very significant for the mathematical community in the future. By the way, you can, there we go. You can download the slides at my blog. And I think I also posted the link on chat so that you can more easily follow the talk. And the slides also have speaker notes, which should prove to be helpful, I think. Okay, before I say anything else, I should probably explain what I mean by formalized mathematics. There's a very old idea going back to Leibniz in the 17th century of characteristica universalis, which is, for Leibniz, this was an imagined completely precise language and a diagrammatical system that would be able to express mathematical, scientific, and metaphysical concepts. And this idea has throughout history caught attention of many people and sparked interest, and it never quite died out. And then around 200 years later, mathematicians made first serious progress in formalization. So one important stepping stone was Gottlob Frege's Begriffsschrift. This was a diagrammatical, formal, completely precise language for expressing mathematical statements. Not too long after that, Bertrand Russell and Alfred Whitehead, this was at the beginning of the 20th century, produced the monumental work Principia Mathematica, where they sought to show that all of mathematics can be reduced to pure logical principles and symbolism. And this work was very inspiring for the development of formal logic in the 20th century. And here they actually tried to develop foundations or basics of mathematics in this very formal style. And then as things developed in the 20th century with the rise of first-order logic, Zermelo-Fraenkel set theory, and other formalisms, it became clear that not only could mathematics be formalized completely, but once it is formalized and once the proofs are written down in this formal language, they can be checked mechanically and completely. And it was stated and believed that this can indeed be done for all of mathematics, and various experiments, small experiments, would show that yes, you can do it. But the question remained whether it could be realistically done on a large scale. And there is no other way of answering the question than to try. So the next important step, which I heard about when I was a student, was a formalization of an entire book of analysis. And this book was Landau's Grundlagen der Analysis. The book was quite appropriate for formalization because the book itself is very detailed and it's quite formalistic in the way it's written, and it has very careful arguments. My teachers never told me who did this, but it was implied that this was a heroic and a slightly insane task, which only demonstrated what everybody knew already, namely that yes, mathematics could indeed be written in a completely formal language. And it was also made understood that now that the point had been made, we could all just proceed with business as usual and forget about further formalization of mathematics, because there is no value in doing so. It's just a waste of time. That at least is very much the feeling, the impression I got when I was a student. Well, but I ended up doing a PhD in logic, so I wasn't really listening that well. Thanks to, so I later learned that the formalization was carried out by Bert Jutting from the Netherlands. He used the automat proof checker, and this was in the 1970s. The source code was luckily preserved by Freek Weidek, who also re-implemented automat in C in the 90s. So we can still verify Landau's book using the original formalization of Jutting today, and it's instant. The entire book is, you press enter and then the machine says, yep, the whole book is correct. So you can see on the right what the formal language of automat looked like. So in a sense, this was a heroic and somewhat insane undertaking. And if you look carefully, the top line states that multiplication is associative, which is Satz, what is this? 226, and this is Satz 222, sorry, excuse my German. Anyhow, you can see here in beautiful German Fraktur that it is indeed about associativity of multiplication. And if you look at the code, you will be able to tell that it is indeed about multiplicativity of, it's about associativity of something called TS, and the proof seems completely incomprehensible. So automat was revolutionary, and it was way ahead of its time, and it made an important point, but I think it wasn't really possible to use it on a large scale. It really, my teachers really were correct. Try to do mathematics seriously in this form was out of the question. So what happened next? Well, computer scientists, not so much mathematicians, but mostly computer scientists, worked on making formalized mathematics practical. And eventually, the idea of a proof assistant emerged. This is a program which assists a human in formalization of mathematics through an interactive process, and together the human and the machine produce mathematics, which is the kind of mathematics that humans want to do, but it is completely verified in every detail because the machine is responsible for that part. So over the decades, various designs were explored, and what you saw going by while I was talking were some fragments of code from the most well-known proof assistants. And one thing to notice is that there is a significant progress since automat, because you can more or less read these definitions. I mean, they're a bit strange, but you can kind of guess what is what, and it's not out of the question that somebody would use this. Okay, so we have these proof assistants. Computer scientists have been developing them now for, well, 50 years. The next thing that I would like to explain is how they work, because if and when you face them, it's good to know what's behind the scene. Now, these are complex pieces of software, and there are many aspects of their design, ranging from user interface to everything else, very computer sciencey things. But we shall focus here just on the things that are relevant and interesting to mathematicians. So how does a proof assistant work? Now, it is important to keep in mind that the real challenge is not the verification itself. I mean, already automat showed that once we do possess the formal proof, then it is easy to check whether it is correct. It really is a question of human-computer interaction. That's the challenge. The challenge is how to make human and machine cooperate on mathematics, given the gap in how humans perceive and work in mathematics and what computers can understand. So to get some idea, what has been done in proof assistance and what has been developed, let us look at a concrete example. Read the following mathematical statement. Do you understand it? Yes, well, of course you understand it. You're a mathematician, right? You can also tell that it's blatantly true. It doesn't really need much thought. Yet, from a formal point of view, the statement is not quite exact. In fact, it is inexact. It omits a number of details. These details don't matter, and your brain can recover them automatically if so desired. But it's perhaps surprising how many details are filled in when they need to be filled in. And the reason I'm explaining this is because this is what a proof assistant must be able to do in order to understand the human. The human is not a robot. The human will continue to speak the way that they are used to speak. So let's try to fill in some details here and see what needs to be done. Well, okay, so first of all, F is obviously some sort of a map, and it would be nice if we could explicate its domain and codomain. And because it says linear, we're presumably thinking of linear maps between vector spaces. So the next thing that you would maybe write that is a little more exact would be something like this. You would say, if U and V are vector spaces and F and U, and F is a map from U to V, which is linear, then, okay, so then what? Well, then 2F of 2x plus y equals 2x plus f of y. But notice also that we put in, we explicitly quantified x and y, and we said x and y range over U. Well, how did we know that x and y range over U? That's because we have f of x and f of y. So if f maps from U and we're going to apply it to x, then x better be an element of U. So here we guessed that x and y are supposed to range over U, because otherwise the statement wouldn't make any sense. We're not done. So first of all, these two vector spaces, they must be over some field. A vector space is over a field, and this field has so far not been mentioned. Well, we're not bothered by that because we all know that there is some ambient field that maybe later on it'll turn out to be a particular one. It somehow doesn't matter. Nevertheless, if we wanted to make this explicit, then the next stage would be something like this, right? You would just say, okay, suppose K is a field, and then you would proceed by saying U and V are vector spaces over K. You see what is going on here? As we're adding more and more detail to the statement, it gets harder and harder to understand the gist of it. It's just getting lost in the bureaucracy. So there is a good reason why people prefer concise imprecision than obfuscated precision. And by the way, we are not nearly done. We need to go on. So what else is missing? To be precise, U and V are vector spaces, so they're structures, right? So they have parts like the operation and the underlying carrier set and so on. And strictly speaking, we need to distinguish between U and its carrier set, which I wrote here as absolute value of U. So the map F really maps from U to V, the carrier sets, and X, Y, and Y don't literally range over U, they range over the carrier sets. There's another possibility here for F. We could also say that F is a morphism from U to V in the category of vector spaces, in which case we would write F, U, arrow, V. But then F wouldn't be a map because a morphism in the category of vector spaces is a map on the carrier set together with the fact that it is a linear map. So such an F would be a little structure that has an underlying function. The morphism has an underlying map and the fact that it's linear, in which case then we would have to write something like the absolute value of F for the carrier of F. Okay, you might think we're done, but we're not done because, for instance, if you look at this number 2 here, the numeral, is that supposed to be a natural number? Well, it can't be literally a natural number because it has to be an element of K. And also, why are we using plus for addition both in U and V? That seems imprecise. So we would have to do maybe something like this. We need to annotate the various parts to tell where they're coming from. So for instance, maybe you need to write a subscript K on the 2 so that it's clear that what you mean is 2 embedded into K via the canonical map, say from integers to K. or it's the addition of the unit of k with itself, something like that. And then also the vector space operations need to be tagged. So, okay, that's the sort of thing that we do. Well, I don't think people actually do this. They can do it if they want to. But if we ever hope to formalize things, then we need programs that can do this sort of thing. Or else we will have to keep explaining the machine details that will completely obfuscate the narrative and what we want to do. This process of going from the simple statement to the more exact one is called elaboration. This is a typical part of implicit mathematical knowledge that is passed on by observation. You observe your seniors to see what they do, and by imitation, you're on your written exam or an oral exam, you pretend that you know how to do this, and then eventually you know how to do this. But this is rarely talked about among mathematicians explicitly, and it's not even talked about among logicians. Logicians are not interested in formalizing this part of mathematical knowledge, at least not the logicians of the 20th century, because they were preoccupied with other problems that were more relevant at the time. Nevertheless, somebody has to attack this sort of question, because elaboration is an essential part of modern proof assistance. It is the bridge between the human and the machine. The people who thought about this very seriously were computer scientists, because they faced similar issues of human-computer interaction in the design of programming languages. And there the question is how to allow the programmer to express ideas, programming, in a very direct way that is not overly verbose. You want to give the programmer the ability to express ideas directly and concisely, much like a mathematician would want. And so these techniques have names. You know them from your everyday life. You know, an assumed ambient field k. Well, that's just called the existential variable in the formal elaboration terminology. Or guessing that X ranges over U, that's called type inference. Automatically changing a vector space to its carrier set as needed, that's called an implicit coercion, or just sometimes a coercion. So these are techniques that have been developed mostly by computer scientists, and that modern proof assistants include, and also many others that I haven't mentioned yet. So if and when you learn your first proof assistant, it's going to look scary because they will be saying strange things like type inference and implicit argument. But keep in mind that you have already seen all of this. It's just been given names and it has been made mathematical. And that's a good thing. You might be curious to see how the statement is written in a modern proof assistant. So here it is in Lean. That's one of very popular proof assistants. If you look at this, you will say, well, okay, it's non-English. It's not too bad. You can see what's going on. I mean, for some reason they keep writing type star. There's some square brackets. We don't understand why some brackets are square and some are not. Obviously, somebody imported the linear algebra package or something. But all in all, it's not worse than LaTeX. I mean, that's a very good sign. It's not worse than LaTeX. It's maybe even better than LaTeX. And by the way, the last line is how you prove the statement. You see, this is an obvious statement. If you have to spend time proving obvious statements for the benefit of the machine, that's a no-go. That's a showstopper. So it's a good thing that proof assistants allow a great deal of automation. And so something like this can be handled by a tactic which is called SIMP, that stands for simple. Okay, let's go on. We have seen this elaboration part. Now let's have a look at oops, sorry, I just mixed up my things here. Okay, so let's have a look at how a typical proof assistant is structured. There are many proof assistants. Not all of them follow this particular philosophy, but most do. And this has turned out to be a good way to design them. Now, of course, a proof assistant has to contain some sort of formalism because it's about formalizing mathematics. But the important bit is that there are two formal languages in a proof assistant. One is called the vernacular, and the other one is the core formalism. The vernacular is designed for humans. It is an expressive language that facilitates the expression of mathematics the way that humans are used to doing. So it will support common mathematical notations, it'll provide support for automation, and it's generally going to accommodate the user. At the same time, it needs to be exact because it needs to be understandable by the machine. So it's a strange mix of something that tries to make the human happy and something that is still understandable by the machine. It's usually quite elaborate and it contains lots of possibilities for organizing your mathematics and so on. We have already seen that there is an elaboration process, and this is called, well, the elaborator does that. It's part of a proof assistant, and it translates the vernacular to a core formalism. The user almost never sees the core formalism. Unless you're a developer of a proof assistant, you are not going to look at the core formalism. But it is the underlying mathematical foundation. It's the thing that people think of as when they say, oh, yes, there is a mathematical foundation. So it should be something that is well understood by logicians and mathematicians so that there is no question about what kind of foundation we're using. And it should also be free of unnecessary complexity. It is important that this formalism is simple. So maybe when you translate from the vernacular to the core formalism, you're going to incur some large factor, like maybe the code becomes 10 times longer. It doesn't matter. The machine can take it. Nobody needs to read it. The important thing is that it is well understood and manageable. And it is designed for computer processing. It's not designed for humans to look at. Now, the actual verification is carried out by a special component of a proof assistant, which is usually called the kernel. This component checks formal proofs. So it doesn't perform any automated tasks. That's part of the vernacular. It's just served the actual proofs and constructions and definitions. And the only thing it has to do is verify that they follow whatever formalism is used by the proof assistant. It is important to understand that this is the only critical component of a proof assistant. So the vernacular might be tens and tens or hundreds of thousands of lines of code, but it doesn't matter if there is a bug in there. Well, a bug is annoying, but it doesn't matter as far as mathematical correctness is concerned. If there is a bug in the kernel, however, then mathematical correctness may be compromised. So these are typically designed to be very small pieces of code. You know, some of them are just a couple of hundreds of lines of code. Some of them venture into several thousand lines of code, which is not a lot. And then they are carefully audited because that's the thing where we put our trust in. Okay, we haven't really spoken about what the core formalism is. What foundation do proof assistants use? Well, here logicians have an opinion. And if you ask any mathematician in the street, you know what the answer will be. They're going to say, well, of course, set theory is the generally accepted foundation of mathematics. And this indeed was the case in the 20th century. And it helped relate all and connect all branches of mathematics. The fact that there was a common ground, a common foundation that also served as a lingua franca in mathematics was immensely important for the development of mathematics. So this is an old and venerable and well understood foundation, which almost all proof assistants ignore. Instead, they use type theory. Type theory was originally proposed by Bertrand Russell, and then subsequently there were several incarnations of type theory. There was Church's simple type theory, then there was Martin Löw's type theory, and then by now we have many variations and derivations of various kinds of type theory. It's a small industry in the computer science community, because type theory also gets used a lot, quite a bit for computer science purposes. In any case, it's a matter of observation that most proof assistants use type theory underneath. Why that is the case is maybe it's interesting to speculate, but it's not something that I want to spend a lot of time on, but I'm happy to discuss this. And I wrote an answer on Math Overflow a while ago where I tried to explain these points more carefully. It's linked in the speaker notes. It seems, but nevertheless, let me see, how am I doing on time? Oh, I'm doing fine. So I can say a few words about this. Okay, so why don't proof assistants use set theory? My first answer is that this is not a matter of philosophy or political conviction or adherence to tradition or trying to break with tradition. This is a very, very pragmatic point. When you're trying to design a proof assistant, you have so many problems on your hands, then trying to be political about your choice of foundation is the last thing on your mind. So you just want to take something that works well. And from what we know, it seems that type theory is in fact a better fit for how informal mathematics is done than formal set theory. Mind you, the thing that you write in your papers is quite far removed from what logicians call formal Zermelo set theory. And that's the thing you would have to implement in your proof assistant if you wanted to use it. You have to implement formal set theory. And there are layers and layers of coding which don't really help anything, you know, like the Kuratowski pairing, and you need to encode natural numbers, sets of sets, and all of that is not really helping with anything. So instead, the designers typically opt for type theory. Another feature of type theory is that more naturally supports large-scale organization of math, and this is very important when you start organizing large libraries of mathematics. In addition, software engineering, which deals with how to organize large amounts of source code, has something to say there and also uses type theoretic methods. So there's an additional benefit there. We can learn from software engineering. One small detail is that type theory treats any kind of construction on equal footing as a proof. So usually in set theory and first order logic, all statements are existential. You don't actually ever construct anything. Now, of course, you can construct things by introducing new constants, which you can then eliminate and so on. But it's good to have from the start good support for expressing constructions. I mean, everything from ranging inductive constructions to any other kinds of constructions. Those are primitive in type theory, and then so they're immediately usable without any additional acrobatics and in translation. Another very, very important point is that a proof assistant must be able to detect not only mathematical errors, but it must also detect typical human errors while you do mathematics. So in set theory, it might be sensible to say something stupid like the sine function is an element of the set which contains numbers 7 and 5. It's a sensible statement to say that a sine function is an element of any set, because you can always say that. It might be false, but it's sensible. But it's not helpful if the machine accepts that sort of thing. In fact, it's really, I mean, quite strange. So for instance, in set theory, formal set theory, if you have a function f, and it's a function of one argument, you're free to apply it to 2 arguments, and you will get a sensible result. And somehow, proof assistants need to be able to cope with that. And so set theory has better support for that, I think. Have a look at my Math Overflow answer where I elaborated on that point. Okay, so if proof assistants have been built and used apparently by some people, there's still the obvious question for the mathematician, which is why formalize at all? I mean, what are you going to gain from formalization? Well, people have been drawn to formalization for various reasons. So let me show you some, and I'm going to do here proofs. You see, this is not a mathematical talk. It's a talk about it's a talk about social norms and social activities of of a community, so I should use appropriate methods. So my method is going to be proof by authority and peer pressure. So why do people formalize? I mean, it looks like little would be gained by doing that. I mean, you get to know that your theorems are correct, but is that so important? Okay, so first of all, there are situations in which it is not realistic that we would be able to check proofs by hand. Even if you had a whole army of mathematicians, it would still be unrealistic that they would spend the time checking some horrible long proof. Let me give you 3 examples. So the famous 4-color theorem was initially proved with the assistance of a computer program that performed a large number of a search, and it checked a number of configurations and made sure that they were okay. They were counted in the thousands. And then it said, yep, the 4-color theorem holds. But nobody proved that the program worked and that it was free of mistakes, which it wasn't, by the way. If you write any reasonable program, there's going to be a bug in it. So a similar situation appeared a bit later with the Kepler, with Tom Hales's proof of the Kepler sphere packing conjecture, where it took a long time to publish the proof because it contained some programs written, I think, in C that were checking many nonlinear inequalities using floating points, and the referees didn't know what to do about that. Now, there were subsequently formalization efforts to formalize these 2 proofs. Georges Contier with his team formalized it in 2005, and this theorem is now completely verified in the Coq proof assistant. So the entire theorem, including all the programs, are proved to be correct, including the execution of the program, which then finds some large number of critical configurations that is beyond the scope of a single human. I mean, I suppose you could check 633 configurations, but by the time you get to 633, you only have a vague memory of what you were doing 2 days ago. So it's certainly better that such proofs are done using computer help. And the Kepler packing conjecture was verified in another proof assistant called HOL Lite, including the nonlinear equalities, without using any floating points. They were using precise interval arithmetic with precise error bounds. An important motivation for the use of proof assistants also comes from computer science. In fact, computer scientists are way ahead of mathematicians in using proof assistants, especially in verifying systems for which security and reliability is of utmost importance. What they do there is that they take a large system and they formally verify that it works correctly. That is to say, each line of code, each piece of design, they state a little theorem about it, about what it's supposed to do, and then they prove that that code actually does what it's supposed to do. And so what you end up with is thousands and thousands of extremely boring theorems, each of which is probably quite easy, but is difficult to compose the whole thing into a coherent whole. And it is impossible to prove all those theorems by hand. You would never want to do that. So one such noteworthy example is CompCert, which is a completely verified optimizing C compiler, which verifies everything from parsing, code generation, code optimization, including the execution on several processor architectures. So this has all been verified. And so these are the kinds of proofs that we cannot do by hand, and we must use proof assistants. There are also people who have simply lost trust in humanity. So here are 2 quotes. Vladimir Voevodsky in 2014 wrote, when he was lamenting about how in some of his celebrated proofs, mistakes were found later, years after they were published. And he said, "And who would ensure that I did not forget something and did not make a mistake, if even the mistakes in much more simple arguments take years to uncover?" And for him, this was a turning point, and he turned away from the Fields medalist work he was doing and devoted himself to finding a new way of doing mathematics, which he eventually found by creating a new foundation and using proof assistance to do it. Another such example, which is a more recent, is Peter Scholz's challenge to formalize mathematics, where he explains that he produced a proof, but then he agonized over it because it was so complex that he couldn't quite see whether it was correct. It was probably correct. It was impossible to get anybody else to check it. It was probably good, but nevertheless, there were some lingering doubts. And so he thought it would be really nice if somebody could formalize this cutting edge recent theorem of his that he considered very important. So it was a new result. It wasn't an old book of Landau's on addition of numbers. This is real stuff. He said, can you formalize this? So this is showing people who have sort of surpassed what humans can do. Another way to view this sentiment, maybe a little more positively, is to say, well, what we're really trying to do is we're trying to break the one mind barrier, what a single mathematician can do. And we're trying to organize ourselves so that we can do more complex things, and we're going to use machines. Okay, so let me press on. A very interesting development using formal mathematics appeared in 2012 and 13 when homotopy type theory was developed. And there I participated. We wrote a book, and the introduction of the book makes it clear that we didn't just write the book, because the mathematics was so new and we weren't really sure how to use the new foundation. We first did it in formalized mathematics. We first used proof assistants because they would guide us. They would make sure we didn't make any mistakes or that we imagined something that wasn't true. And after we gained enough experience using formal mathematics and proof assistants, then we proceeded to unformalize everything we knew and wrote the book so that the rest of the mathematicians, including ourselves, could understand what was really going on. There is a third, maybe the most important reason for using formalized proof assistance and formalized mathematics, which is simply to recognize the immense potential that such approach can have. We're not there yet, but if you imagine a future in which machines can really help mathematicians, you see that this future is going to be completely different. It will transform mathematics. And some people don't want to wait, and they want to do it now, and they are willing to devote their time to do it. And Kevin Buzzard is spearheading one such important effort, which I'm going to also mention a little later. So, okay, there are some enthusiasts who are doing this, and computer scientists are doing their own thing, but will formalized mathematics go mainstream? I think this is completely the wrong question to answer. This is like thinking that computers are not going to barge into mathematics and change it. Of course they will. The question is, when will formalized mathematics go mainstream? Well, you could look at charts and say, okay, how is it growing? And if you look at one of the libraries of formal proofs, it's called Archive of Formal Proofs. It's growing at a rapid pace in what looks like an exponential growth. This is the kind of exponential growth that we can be happy about, not for a change, not fear. And so we can say, well, okay, but I don't think, it's big, maybe it'll grow bigger. I don't think it's really so much that the size matters. It's more that the potential for disruption is important. So to wrap up, I'm going to show you a little picture of what formalized mathematics looks like and how mathematicians work on it. We're going to see activities of mathematicians working on the lean mathematical library called MathLib. This is the project that is led by Kevin Buzzard. And you will see little figures going around, that's mathematicians. And then there is a tree growing, that's the library files in the directory structure. And then there are these arrays. This means that the user has changed the file. You will see these flashes when a power user does something to all the files. And you can see the date, how it's growing this is what formalized mathematics looks like. It's pretty, right? It's nice. But does it tell us anything? Yes, I think it does. Watching this, you realize that this is not separate groups or 2 or 3 of mathematicians, each belaboring on a paper of their own. It's not like that. This is not anymore the medieval mathematicians guild, which is how mathematics is still organized today. This is a post-industrial division of labor. It is completely new. It's a math hive. It's exciting. And we haven't seen this sort of thing before, and I think it's going to change mathematics. When? Now. So as I was preparing the slides for this talk, an article in Nature came out, and it's bombastically said, mathematicians welcome computer-assisted proofs in a grand unification theory. You know how it is with these popular science general audience papers, articles. Well, behind it is a blog post by Peter Scholze, who half a year ago posed a challenge to the formalization community, in particular to the MathLib and the Lean community that I just showed them their hive. He said, okay, here's an important theorem of mine. That's the one that he was belaboring and was worried whether it's true. Can you formalize this? And only half a year later, he said, this is amazing. It's been done. He expected that things will have to be carefully divided up and teams of people would work. But no, a relatively small group of people took up the challenge and they formalized it in half a year, which is comparable, say, to actively reviewing a complicated paper, except that now, instead of just having the good word of the trusted anonymous reviewers, it is completely true, verified in every detail, and put on unshakable grounds. So I think this is a lot better. It is the glimpse of the future. It's the true cooperation of man and machine. If you're curious and you'd like to try to know where to go and how to try things, I'm just going to point you in one direction. There are many proof assistants. So maybe if you are interested in constructive mathematics or computer science, you can go look at those other proof assistants. But if you are a mathematician participating at the Congress, then I would say your best bet is to just go and find the Lean community. They're a friendly bunch. They're working hard. It's growing. It's got thousands of users, and you can always find help on their chat system. So with that, I'd like to finish. Thank you.